Hello everyone, welcome to Chapter 3, Derivatives. Here we talk about differentiation rules in this section. And there are plenty of rules, as the title says, that helps us to do the differentiation, to find the derivatives a lot quicker, because that's what rules do, right? They are shortcuts to help us achieve the goal. And so to kind of illustrate how this works, let's assume that y equals c, okay, is our graph. Y equals c is a horizontal line passing through c. Okay, if c is 3, then it is y equals 3, a horizontal line passing through 3, and so on. Could be any number. So if I wanted to find the slope of this line, right, the slope of the curve at a point. Now this is not a curve, it's a line, but you know that a line is a special case of a curve because it is a polynomial here of degree 0 here, right? The degree is 0 because there is no x term here. The degree is 1, then it is a line which is slanted, but here it's a horizontal line. Now, if I chose, say, a point x here, and that will be x comma c, right? And if I moved about h units away, and this was my point x plus h, then this would be x plus h comma f of x. But you know, f of x here is nothing but c. So it will be f of x plus h comma c, because you're still on that same horizontal line. So no matter what x value you consider, the corresponding y value will always be a c. And we also see that because it's a horizontal line, the slope of this horizontal line is 0, because we know that slope of the curve at a point is the same as slope of the tangent line at that point. And we see that for here, if my point of interest was x comma c, the tangent line there will be that horizontal line, right? So it's the slope of the horizontal line because the tangent line coincides with the graph, the pink graph itself. We know the slope of any horizontal line is 0. So if I were to rewrite this in derivative notation, d over dx, right? Remember that notation? So we also saw df over dx, right, as a function. In this case, it will be dy over dx. And we replace y by what is given. Y is nothing but c, isn't it? So d over dx of c. So the derivative of a constant is 0 because y equals c is a constant, right? It's a number. Derivative of a number is 0. That's what this means. We get the idea from the graph, but we're able to build it up to a rule where we say it doesn't matter what c is. If c is a constant, if it's any number, then the derivative of that number will always be a 0. You can support that idea by understanding that we're trying to find the slope of the horizontal line. That is the reason why it will always be a 0. So it's things like these that we will use, or mathematicians used, to build up the rules. Okay, so I'm going to put up the rules for us, and then we will go over them one by one. I'll quickly describe what they stand for. So here are the rules. Let's go over them one by one. So we know d over dx. That format simply means derivative of a function with respect to x. That's how you understand it, right? Because the x is the variable, so we understand that it's with respect to that variable. If the variable was t, then it would be derivative of the function with respect to t. So here it's d over dx of c. C is our function. It's a constant function, and so it's called the constant rule because derivative of a constant is 0. Now, if you had a function x power n, it's called a power function. If you had x power n format of your function, the derivative of that would be n times x power n minus 1. So this is again a shortcut to help us to find the derivative. Again, I want to reinstate that finding the derivative traditionally, originally, is by using the limit of dq, right? So if you're given a point, you look for a corresponding, you create another point basically, and then using the h, and then you find the limit of the dq, the h is cancelled off, and if you have the point, you plug in for the point. If you don't have the point, you at least found the derivative of the function. And so all that process is reduced for us here when we use these rules appropriately. Now the third condition says d over dx, derivative of c times u. U is a function of x, okay? U is a different function. So what we're saying is c times u means that the constant will not be impacted by the differentiation process, which means you can pull that constant out, as we can see here. But you will only take the derivative of that u, because u is a function of x. U is some function of x. U involves x within it. Therefore, you need to differentiate it with respect to x. C does not have x in it, therefore the constant can be pulled out. Then when we go to condition number 4, it's a derivative of a sum of two functions that are functions of x. So derivative of u plus v, that is very intuitively derivative of u plus derivative of v. And notice how my u is smooth and my v has a little twirl there on the top, so that I differentiate between my u and my v. You really want to be super careful here. It's also case sensitive, so we're using all lowercase letters, so watch out for that. And it's called the sum rule, and we also indicate that u and v are functions of x. Okay. They're not the same functions, therefore I call u as f of x and I'll call v as g of x. And if you had derivative of u times v, as you can see here, it's called the product rule, and it's got its own little rule here. You'll take the u times the derivative of v plus v times the derivative of u. Okay. And the last rule you see here is called the quotient rule. And as the name says, if you took the derivative of u over v, and you have this slightly complicated expression here, v times du over dx minus u times dv over dx all over v squared. There is a derivative, there is a derivation, to this, meaning this formula is derived from, from other concepts, and that is not completely explained here for you. We're just using the rules. I'm showing you the rules. But the reason why it looks complicated is because of that derivation. A quick recall on how we write the derivatives. If it was the first derivative, the first time you derive it, we use these notations more regularly, dy over dx, or y prime, or f prime of x. And then if it's the second derivative, meaning you found the first derivative, which is dy over dx, and if you took the derivative of it again, then that is written as d squared y over dx squared. Okay. On the top, the 2 is in between the d and the y. In the bottom, it is outside the x. Y double prime, or you can, if you write in the f notation, f double prime of x. Then the third derivative, that will be d cubed y over dx cubed. That's got y triple prime plus f triple prime of x. Once we go to the fourth derivative, it's going to be hard for us to write those 4 strokes, right? The prime notation becomes harder after 3. So up to 3 we have this, and for anything beyond 3, we just use the n notation in parentheses. So for the nth derivative, dn power y, dny over dx power n, and we put the n in parentheses, otherwise it will become y power n, right? So to avoid any confusion of that sort or misunderstanding of that sort, we use the n in parentheses. So these are some other notations you will see that we might want to use in certain circumstances. And so generally speaking, you see the dy over dx notation or the prime notation. So I want to give you the same rules in prime notation, just so that you get familiarized with those versions as well. So I'll say in prime notation, the stroke, right? Derivative of c, meaning c prime, is 0. The first derivative, right? So the derivative of x power n is n x power n minus 1. And as you can see, the prime notation is so simple, it's easy to use, but we have to be super careful about the way we apply it. So cu, the whole prime, is you're taking the derivative. So the way you read this is derivative of cu. But the answer for that is c times derivative of u. So I just want to write that here. That means it is the derivative of cu. Here it means c times the derivative of u. And so it makes a drastic difference in the way we take the derivative. So u plus v, if you took the derivative of the sum, it said it's derivative of u plus derivative of v. Derivative of uv is derivative of u times v plus derivative of v times u. So u prime v plus v prime u. I like the prime notation because it's just easy to remember for me. Okay. U over v prime will be u prime v minus v prime u all over v squared. So our first problem says find dy over dx where y equals 7. So for dy over dx, in the place of y, we replace the y by what is given to be, y is given to be equal to 7. So now we see that derivative of a constant will definitely be 0. There is no x in it, right? So you can clearly see that you're taking the derivative of the slope of a constant of a horizontal line. So all those things come in, and we know that it's because of the constant rule. Next problem says find dy over dx, and y is given to be x cubed. Once again, dy over dx is what we need to find, and in the place of y, I plug in x cubed. Then I go back to the rule that says if I had x power n, right? If I had x power n, that's the second rule, then the power rule says it's n times x power n minus 1. N times x power n minus 1. So the power times x power 1 less than the power. So that's going to be 3, the power, times x power 3 minus 1, which comes out to be 3x squared. And this is our power rule. Okay. Now I want to quickly give you the importance of these rules. These rules make our life so much easier, no doubt. But if you were to do it in the original traditional way of finding the slope, then what you would have done is you would have y, which is like your f of x, right, to be x cubed. And you will need an x plus h, which is x plus h the whole cubed. And so if we wanted to find dy over dx, it will be the same as limit h approaches 0, f of x plus h minus f of x all over h, isn't it? And this is what we would have done if not for the rule. So you might be asked to go back to do this because that is the origin of this whole concept. So it's x plus h the whole cubed minus x cubed all over h. And then we know x plus h the whole cubed will have to be expanded using the formula or by multiplying it 3 times over. And that comes out to be, well, it's a cubed, so x cubed plus 3x squared h plus 3x h squared plus h squared minus x cubed, minus x cubed all over h. This is how the formula works. Okay, so now you have the x cubes going away. We know that these are the terms that contain h in it. So that's going to be 3x squared plus 3xh plus h squared all over h. Cancel those off. And now we have limit h approaches 0, 3x squared plus 3xh plus h squared. And when you allow h to approach 0, this term goes away, right? Because it's got a 0. Got an h in it, so it's going to become 0. This also becomes 0. So upon applying the limit, we get 3x squared as our answer. And what you see up here was the same thing, 3x squared. We just got that in a jiffy, right? We didn't go through this entire process. Therefore, we should be super thankful for these differentiation rules because they help us to get to these answers so quickly. But the derivation of these rules actually require more advanced understanding of calculus. In some cases, it requires logarithmic differentiation, a concept that you'll be looking at in calculus 2. In some cases, it just involves, the same limit of dq, but then it'll be a slightly different approach to manipulate it to get the formula. What I mean by that is for your, let's say for your product rule, right? For a product rule, uv prime. So what they'll do is they'll do the limit of h approaches 0, uv plus h, f of uv plus h minus f of uv all over h. So that's how they will try to derive those things. It can get a little complicated, but I want you to understand that it's all coming from this original idea, and therefore we always look up to this idea. But then over time, we want to do things quickly, and so we have a newfound respect for these differentiation rules. I just wanted to drive home the point there as to the ease and the convenience of these rules. And that's the whole idea of math, actually, because math has so many rules and we sometimes, dislike it for that. But rules only mean that these are shortcuts to get to your answers. As long as it's valid and you're following all the premise of those rules, we should be fine. We'll get to places we need to get to quicker. All right, so here's differentiate. And it says x power 2 over 3. And notice the language here. It says differentiate, which means they want you to use the process. Right? The process of finding the derivative is called differentiation. So, differentiate actually means to find the derivative. And they didn't say explicitly dy over dx. But we know that we're trying to find the derivative with respect to, the WRT stands for with respect to the variable x. That helps us to kind of do this as dy over dx. There is no y in the problem, so then, you can write it as dy over dx. Or if you didn't want to introduce something that was not in the problem, you'll simply say derivative of x power 2 over 3 with respect to x. So d over dx of x power 2 over 3. Okay, now if it's a differentiate t power 2 over 3, then it has to be with respect to t. So it'll be d over dt, t power 2 over 3. And so when they do not give you much details, it really helps us to see how we interpret the problem. All right, so I'm going to find out d over dx of x power 2 over 3. You can put that right next to the d, or you can put it outside that fraction d over dx, okay, if you want to see the function very explicitly. Now, the power rule allows us to, that's for any power, right? So 2 over 3 x power 2 over 3 minus 1. Write that 3 properly. Should be pretty strong in your fractions. Therefore, 2 over 3 x power 2 minus 3 over 3, right? When you take the LCD. So that's going to be negative 1 over 3. But you know that in math, we do not like to express our answers with a negative exponent. So go to the rules, the laws of exponents. We have like 7, 8 laws. Laws of exponent tells us that for negative exponent, you flip the base and change the sign. So the x moves to the denominator because it's in the numerator, it moves to denominator, and then the sign becomes positive. Flip the base is x, so flip the base and change the sign. And also we know that we like to rewrite this whenever it's simplified in the radical notation as possible. So this is nothing but the cube root of x. You can leave it like that also. So it just depends on how they want your answer to look. You can put it that way, or you could write it in the radical notation. Differentiate x power root 2. Now, we should not blindly use the rules, so we always want to make sure that the rules are followed carefully. The rule for the power rule, right, the one that we're just using, for the power rule is that the power has to be a constant, must be some number, a constant, not a variable. So look at x power root 2. Root 2 is a constant, right? It's an irrational number. It's a number. It's not a variable. It's not some other letter. Therefore, we can use it. So although it looks a little strange, we can totally use the power rule. And so d over dx of the given function, x power root 2. I'm not introducing a y. You are totally welcome to do that, for which you'll have to say let y be equal to x power root 2, and then you could do dy over dx. I'm saving a step there by just using the given function as it is. So that's going to be root 2 x power 1 less than that, right? So root 2 minus 1. Okay, now we have to be super careful. It's square root of 2 minus 1. The minus 1 is not under the radical. It's outside the radical. So don't rewrite it as square root of 1 and therefore 1. That won't work, right? Square root of 2 is like 1.414. So that minus 1. So it's x power 0.414, etc. So it's totally different if you didn't understand or didn't put the notation properly. The square root is only for the 2. The symbol, the radical sign is only for 2. Find dy over dx, and we're given y to be 1 over x power 4. Okay. 1 over x power 4. Now there are several ways to approach this. Okay. So once again, in the place of y, I want to introduce the given function. So you can see this as a quotient, right? A fraction, and you could use the quotient rule. But remember, the numerator for this quotient is a 1. So we can use the quotient rule if you have something else on the top, another x version expression. It is just a 1. So we can actually reduce this, the complicated expression or the rule for quotient rule is simply using the negative exponent rule and say, okay, I have x power 4 in the denominator. If I flip the base and change the sign, it will become x power negative 4, bringing it up to the numerator. Right now, the fractional form is gone, and we have now a power form. So we can use the power rule instead of the quotient rule. It's not wrong to use the quotient rule. It will only be lengthy, more cumbersome for us, so we're trying to reduce that here. So that's going to be negative 4, x power negative 4 minus 1. And that will be negative 4 x power negative 5, isn't it? As always, we try to rewrite the answer without the negative exponent. That will be x power 5 because you flip the base and you change the sign. Find dy over dx. Y equals x power negative 4 over 3. dy over dx, which is the same as x power negative 4 over 3. So it's negative 4 over 3, x power negative 4 over 3 minus 1. Negative 4 over 3, x power negative 4 minus 3 is negative 7 over 3. And once again, you have negative 4 over 3 in the denominator, but they'll get the x with a positive 7 over 3. Here is a case where I want to leave it as a fractional or a rational exponent. And usually, personally, how I decide this is I go by the question. If the question left it as a fractional, in a fractional form, then I will leave the answer also in the fractional form. If it appeared as a radical form in the question, then I will return it in the radical form. But sometimes, it's just the instruction of your problem or the simplicity of the expression that you want to write it that way. Like this could be, for instance, rewritten as cube root of x power 7. But you can see that that looks a little more complicated. But again, go by what the question asks for and understand that these are equivalent answers to this problem. The next one says find dy over dx, where y is square root of x power 2 plus pi. Now this is a question where you have to rewrite this in a form that is manageable first before you can apply the rule, because right now there's no rule with a radical like that, right? No differentiation rule. So here is the underlying rule for all that you do in calculus. Algebra before calculus. Or if it's a trig function, usually trig before calculus. That's the underlying rule in all of these. See what algebra can do to simplify your expression before you apply calculus. That way it is completely manageable, and we've seen that all along, right? For instance, when we were trying to find the limit, we applied calculus and we found the limit. But in order to apply the limit itself, we ran into some conditions where the denominator became 0. So in those cases, you got it as 0 over 0. So what we did then was we used algebra to get past it. Like we used the conjugate technique. Sometimes we used the LCD technique and things like that to overcome it. So now you have here the square root for this x power 2 plus pi. But we know that square root is written as power half when you write it in the rational notation as a ratio. So that makes it a whole lot easier when you see it like this, x power 2 plus pi over 2, because we know that the product rule of exponents, right? Meaning, and you have, or I should, in this case, I should say power rule, not product rule. The power rule of exponents says that if you had powers stacked up, right? The x has the power stacked up, right? You have the 2 plus pi, which in turn is stacked by 1 over 2. And powers are stacked up, we multiply the powers. So you should be pretty strong in your exponents. So if it's a power m, which is stacked with power n, it's the same as a power m times n. And that's the idea here. So you can keep it like this, or you could simplify it. It's your call. But remember, again, all this was before we actually applied calculus, which is to find the derivative. Okay, now that I simplified the algebraic portion of it, I can now do, so I look at 2 plus pi over 2, which is in the power, and I know that this entire power will give back a number, a constant, right? Therefore, I can use the power rule of differentiation. Because remember, we have the same names for all these types. We have power rule for exponents, we have power rule for logarithm, we have power rule for differentiation, as we just saw, isn't it? And so because of the same rule name type, you have to always indicate what it is coming from. Is it the power rule of exponents, or is it the power rule of differentiation, and so on. Anyways, coming back here, the power rule of differentiation says I have to have a constant. I cannot accommodate any variables. Pi is not a variable. Pi is an irrational number, approximately 3.14. So you have that expression when you expand it, 2 plus 3.14, so 5.14 divided by 2. So it's going to give us a number. Therefore, we are free to use the power rule of differentiation, which is 2 plus pi over 2, x power 2 plus pi all over 2 minus 1. All right? So that will be our power rule of differentiation. So that's 2 plus pi over 2. Let's keep it together there. Focus on the power here. So if I separate these fractions, so I get 2 over 2 minus pi over 2 minus 1, right? 2 over 2 is 1 itself. So 1 minus 1 will be 0. So those two will go away. And that helps me to come back here as 2 plus pi over 2 x power negative pi over 2. Now negative pi over 2 should be brought down. Right? Did I get a negative answer? Sorry, there was a plus there, so it must be a plus everywhere. Okay, so that is x power pi over 2. So we have 2 plus pi over 2. X power pi over 2. You can leave it like that, but I want to come back to the question, and the question has the expression in the radical form. So I want to do that. When the denominator is 2, you know it is radical. So that's going to be square root of x power pi. And I can leave my answer like that. Okay, we can just box this as the final answer. Find dy over dx. And y is given to be x power 4 plus 12x. All right. As a first step, replace your y by this expression. You see that plus in between those two terms. It's a polynomial. You have the plus. So before you apply the power rule and so on, first we want to use the sum rule so that we can write them as sum of two terms. So I just say sum rule. And then for this one, we could use the power rule. So let me just write that down. 4x power 4 minus 1. So I'll just say power rule here. Whereas here, I can use the constant multiple rule, which says I can pull out the 12 and just do d over dx of x. So here I'm using the constant multiple rule. And all this is to do with the differentiation. So I'm just going to put that name of the rule there. And that's going to be 4x cubed plus 12 times. Here, you can see it in two ways. Dx over dx will be 1. But you can also see this as a power rule where x has the power 1, right? So this is 12 times 1 times x power 1 minus 1. And we know that that's going to be 1. 12 times 1 is 12. X power 1 minus 1 is 0. But laws of exponents says x power 0 is equal to 1. Right? Zero exponent rule says anything power 0 is 1. Therefore, you get back your 4x cubed plus 12. 12 times 1 plus 12. I did it elaborately for you to see all the steps there. But eventually, we'll just say, okay, dx over dx will be 1. We'll come to that understanding as we process through other problems. Okay. But for now, we want to remember that this was from zero exponent rule. And you can clearly see how algebra is an integral part of calculus. You really cannot survive in calculus without being strong in algebra. Find dy over dx. And y is x cubed plus 4 over 3x squared minus 5x plus 1. And eventually, you'll be doing faster than what we're doing now. They're just being introduced to this concept. So it's a good idea for you to pause the video and catch up with me later. So I want to use the sum rule to separate them. And I'd like to also, at the same time, just to save time, I'm going to pull out the constants. and only focus on the, and you can see that it's d over dx of 1 for the last term, right? I want to leave it like that so you can see it as a constant rule. Constant derivative of a constant is 0. And so that's going to be yeah. So I kind of, slow down a little bit here. I didn't do the 3 minus 1. Instead, I wrote it as 2 for the power here also. Instead of doing 2 minus 1, I just wrote it as 1. And you can clearly see that we applied different specific rules here. So quickly to indicate that, that was power rule. And here we had like constant multiple, right? Because we pulled the 4 over 3 out in the beginning. So constant multiple plus the power rule. We did both. Here too it was constant multiple rule. And this was just the constant rule, because derivative of a constant is always a 0. So we used, in some cases, specific rules. In some cases, we did a combination of rules. Nevertheless, we want to get this expression derived. And so that's going to be 3x squared plus 4 times 2, 8 over 3x minus 5. There is 0 not included in this. And you can immediately appreciate how helpful this rule is, because if you didn't have this rule, you would have done x plus h the whole cubed plus 4 over 3x plus h the whole squared minus 5 times x plus h plus 1 minus this whole thing divided by h, and you have to find the limit. Limit of dq would have been that huge expression. So we're very, very glad that we have this. Ooh. Okay, here comes the next question that is more of a critical thinking style. So let's say, does the curve y equals x power 4 minus 2x squared plus 2 have any horizontal tangents? If so, where? I want you to think about this. Okay, x power 4 minus 2x squared plus 2 clearly is a polynomial. So that means it's continuous. It's a curve. And we're saying, do you know if there are any tangents? Here comes our critical thinking question. Does the curve y equals x power 4 minus 2x squared plus 2 have any horizontal tangents? If so, where? Do we agree that this is a curve? So look at the expression. It's x power 4 minus 2x squared plus 2. Clearly, that's a polynomial of degree 4. You know it's going to go up and down. In fact, if you recall from your pre-calculus lessons, the end behavior of this polynomial is also apparent. The leading term has a leading coefficient that is positive, and with an even degree of 4, you know that your ends will either point upward or downward, but with a positive leading coefficient, you know it's both going to point upward, and you're going to have 3 terms, because the number of terms is always 1 less than the degree. The degree is 4, so there'll be 3 terms. So, ideally it's going to look like a W, right? It's not going to look like that. Maybe it's going to look like this. But nevertheless, it's going to be roughly like a W shape, as exaggerated as it may come. But you know that it's got to have 3 turns like that. Right? And depending on, multiplicity and those other conditions, you might not see some turns very explicitly, but, because of the repetitiveness, the multiplicity of it, that there are so many turns happening there, or so many x-intercepts happening. Anyways, all that was from our pre-calculus. But coming back to this question, we know that this is a curve. So our question is, if I had something like this, they're asking us, does this curve have any horizontal tangents? So what are horizontal tangents? These are horizontal lines at certain points on the curve. So I'm thinking, okay, at this point, we can have a horizontal line, right? Because that line passes through that point on the curve where the tangent to it is a horizontal line. We could have one here. We could have one here. So we're asked to find where these horizontal lines can happen, or horizontal tangents. Okay. So as I mentioned before, horizontal tangents are horizontal lines at certain points on the curve. So if you look at this, you can clearly see that the slopes at these points, right, where the horizontal line passes, slope of a horizontal line is always a 0. So the tangent line, the horizontal tangent line at these points must have a slope that is 0. Let's write that. This implies horizontal tangent lines must have their slope as 0 and put the 0 itself at those points, right? Whatever those points are. So technically, at each one of these points, the dy over dx, so if you took the derivative at those points, right, that should be 0, because we know that the derivative is the same as the slope of the tangent line, or the slope of the curve at that point. So I'll just put slope here, okay? So technically, we are trying to find this dy over dx, but then we are told that d over dx, we're told that y is x power 4 minus 2x squared plus 2. Put that in here. And you need to set that equal to 0. Okay. So now take the derivative. That's going to be, we can move fast if you wanted, meaning you could write them as separate derivatives because of some rule, or you could see them as some rule happening followed by the individual power rule or constant multiple rule or constant rule. So if you can see it that way, you can see that this actually becomes 4x power 3 minus 2 times 2x power 1 plus derivative of 2 will be 0. And you're setting that whole expression equal to 0. Yeah? So that's basically 4x cubed minus 4x equals 0. Then it becomes pure algebra for us because we already anticipated these slopes at these points to be 0. We're trying to find what those points are by setting the derivative to 0. And then, we have, whenever you have this, let me quickly warn you that you shouldn't be actually doing this. Plus 4x. Do not do that. Because in algebra, when you have a polynomial like this, we always factorize. Okay? Factorize polynomials. That is very, very important. Otherwise, we'll lose one of the x's. We lose the power. So 4x is pulled out. We're left with x squared minus 1, which is equal to 0. Always factorize. So x squared minus 1 is difference of squares. So that's x plus 1 times x minus 1 equals 0. Okay. Now, if you look at this, 4x cubed minus 4x equals 0, before we began to work on it, that was an expression, a polynomial with degree 3. Therefore, when you solve, you should have 3 answers for x. That's how you account for it. Now, if you did the plus 4x on both sides, then you would divide by 4x on both sides, thus eliminating one of the x's. So your answer will only have 2 x values. So that is the reason why we have to be super careful about factorizing. All right. So this implies that by algebra, the zero factor property, you set each factor to 0. If you want, you could also write it as 4x equals 0. Then this factor is set to 0. And so the zero factor property says that either 4x is 0 or x plus 1 is 0 or x minus 1 is 0. So solve for them simultaneously. So divide by 4 on both sides, you get x equals 0. Subtract 1 on both sides, you get x equals negative 1. Add 1 on both sides, x equals 1. So you have 3 values. Okay, x equals 0, x equals negative 1, and x equals 1. So we say this implies the curve then has horizontal tangents at these points, right? We got those 3 points. In fact, we see it's all lining up because we anticipated a W shape with 3 turns, and then at those 3 turns, we have the 3x values. So the curve has horizontal tangents at 0, negative 1, and 1. So you want to find the corresponding points because the question says, if so, where? Where meaning we only found the x values. So the corresponding points, sometimes they'll only ask for x values, which is fine, but we want to find their location. So you want to give their coordinates. So when x is 0, your y, plug in for x as 0. So x power 4 minus 2 times x power 2 plus 2, isn't it? And there we want to insert our 0. And that gives us a 2. So this implies that coordinate is 0, 2, right? X, y. Do the same for x equals negative 1. Negative 1 power 4 minus 2 times negative 1 squared plus 2, which comes out to be 1. Therefore, the coordinate is negative 1, 1. And then x equals 1. Because the powers were even, it comes out as 1, 1. Same thing here. So the way I drew my W, maybe it's not exaggerated, but because of the symmetry that you see here, it is probably a nice W. Maybe that's the graph. Okay. So then you have a horizontal tangent at 0, 0, 2. Then you have at negative 1, so this could be 1, this could be 2. So this could be negative 1, 0, 1. We have horizontal tangents at these points. Yeah. And we'll wind up with the last problem here. In fact, we could do a couple more problems because I don't think we did a quotient problem. So let's, squeeze in 2 or 3 problems. So let's do find the derivative of, and I'll just do a few problems here. So the first one is, let's use a z. We're so using x and y. 4 minus 3x over 3x squared plus x. So we want to find the derivative of this. Remember, this is derivative of the function z with respect to x. So dz over dx, which is the same as replacing the z with 4 minus 3x all over 3x squared plus x. And clearly you have x on the top and x in the bottom. So we want to think of this as the quotient rule. So the numerator could be your u and this could be your v. So u is a function of x. And v is a function of x as well, which is 3x squared plus x. And du over dx would be derivative of 4 is 0 minus 3 times derivative of x will be 1, which is negative 3. And dv over dx will be 3 times x squared, right? So that's going to be 2x. Derivative of x squared is 2x. Plus derivative of x is 1. So that's going to give us 6x plus 1. Okay. So now that I have the individual derivatives, I can go into the formula here, the quotient rule. I'd like to keep it as u and v. And we know that this is u prime v minus v prime u all over v squared, if I use the prime notation. If I did the high d low condition, so then that'll again be expressed the same way. So I'm going to keep it like this, okay? U prime v minus v prime u. So if it helps, we can write this as u prime, and this is v prime, okay? So u prime will be 4 minus 3x. Oops. U prime is negative 3. Negative 3 times v, which is 3x squared plus x, minus v prime, which is 6x plus 1, times u, which is the torque, all over v squared, 3x squared plus x, the whole square. All right, so that has to be distributed. That gives us negative 9x squared minus 3x. Then remember the minus here outside when you FOIL. So that's going to be minus 24x plus 18x squared minus 4 plus 3x all over 3x squared plus x, the whole squared. Okay, so the 3x minus 3x and the 3x will go away. Combine the like terms that we have. And that gives us 9x squared minus 24x minus 4 all over 3x squared plus x, the whole squared. That's all you can do. So just box the answer there. That helps us with this. Now, in terms of the high D low, let me quickly explain that as an easy tip to remember. Some of you remember this from high school. U over V, the whole prime, okay, can be written as high over low, the whole prime. Low D high minus high D low over low squared. Low D high minus high D low over low squared, where the low is your one in the bottom, which is your V, and high is your U. So if I were to write this, if you recall here, it's U prime V minus V prime U over V squared. That's the way, that's easy for me to remember. But you can think of it as low D high minus high D low. Okay. All right, class. We'll look at another example now. Find the first and second derivatives and we're given s equals t squared plus 5t minus 1 all over t squared. So, if you think of this, the variables are s and the t. S is written in terms of t, right? Let's make a quick observation there. S is written in terms of t, which implies s is a function of t. Keeping this in mind, we know that we have to derive s with respect to t. Derive s with respect to t. Okay, remember the shorthand for that. So ds over dt gives me the first derivative, which is to write this expression all over t squared. And for this again, there are several ways to do this, meaning you could do the quotient rule here. You can apply the quotient rule. But because of the setup itself, I feel it'll be a whole lot easier if I divided each term by the t squared, right? Because I'm using algebra to simplify this. So in the first term, it becomes d over dt. I'm not even applying the derivative yet. That's going to be 1 plus 5 over t, right? Minus 1 over t squared. Now I can move all the t up using the exponent rule and say that's going to be 5t power negative 1 minus t power negative 2. Because then I can skip the quotient rule altogether and use the power rule. So now if I apply the derivative for each term individually, that will be derivative of 1 will be 0 plus 5 times derivative of t power negative 1 will be negative 1 t power negative 1 minus 1 minus negative 2 times t power negative 2 minus 1. So that's going to be negative 5 t power negative 2 plus 2 t power negative 3. So that's my first derivative. Okay. For answer purposes, you will rewrite this as 5 over t squared plus 2 over t cubed. Okay, that's your first derivative. Let me box that part. I like to keep it in the exponential, the negative exponent here. Let me rewrite on the left side that this is nothing but ds over dt. So that's your first derivative. They wanted us to find the second derivative. That's going to be d squared s over dt squared. So you're going to use this expression and take its derivative. So d over dt squared, and that's going to be on the top, negative 5t, the t power negative 2 plus 2t power negative 3. Now take the derivative of this first derivative, because that will be your second derivative. That's negative 5 times negative 2t power negative 2 minus 1, right? Power down times t power 1 less than the power, plus 2 times negative 3 t power negative 3 minus 1. So that makes it 10 t power negative 3 minus 6 t power negative 4. And then we write that also as positive exponents. And that will be our answer for the second derivative. First derivative and the second derivative. We find that that's really very interesting. Now, can we find the product rule for 3 terms? Yes, we can use an extension of the product rule. So this next problem will be the last problem, where I kind of show you how we can apply the product rule when you have 3 things to multiply, because we've seen only product rule for 2 things to multiply. So you have the u prime v plus v prime u. But if I had u, v, and j, let's say, how would you do that? So that's this problem. For k of x, which is x minus 1, the whole x minus 1 times. Hold on. It says find the derivative of k of x. Okay, how do we do this? I'm going to use the prime notation, okay? So if I have 3 functions, okay? So let's say k of x is u, v, and let's say j, u times v times j, okay? If you want w, we can use w. u, v, w, is that helpful? Okay. So if I have to find k prime of x, which is u, v, w prime, okay, that is done by doing this, okay? So that will be derivative of the first one times v times w plus derivative of the middle one times u times w plus derivative of the third one times u times v. That's it. So that is what we're going to do here. Okay. So let's call x minus 1 as u. V could be negative x squared minus 2x. And w will be 2x minus 2. So this means that u prime, take the derivative of that, that will be just 1, right? Because it's 1 minus 0. So that's going to be 1. Derivative of v prime will be negative 2x minus 2. It might seem a little fast for some of you, so please pause the video, do the derivative by hand yourself, and see if it matches here. Okay, so I'm using the power rule. I'm not showing it to you explicitly, but I'm taking the derivative term by term to get my individual derivatives for u, v, and w. W prime will be just the 2, because derivative of x is 1 and the derivative of minus 2 is 0. Okay. Now it's time for us to find the k prime. So u prime, which is 1 times v times w, so negative x squared minus 2x times w, 2x minus 2, okay, plus v prime u times w, v prime, so that's negative 2x minus 2, v prime times u times w. And the third one was w prime, which is 2, times u times v. I know it looks lengthy, but it's definitely manageable because it's algebra. You'll have to FOIL it. Well, I'm going to keep the first term as it is and FOIL these two terms. And here I'm multiplying the 2 with the x minus 1. And in the next step, I plan to FOIL it. Okay, as I was doing this, I made a quick correction. It's 2x minus 2. I wrote it as minus 1. Because when you actually FOIL it, the 2 should be minus 2. All right, so I got negative 8x cubed. And in fact, all of these will go away. Okay, negative 4x squared with the positive 8x squared. And then 2 and the 2 positive, that's positive 4x minus 4x squared. So those go away. So all the x squareds basically went away. Okay. And then we have to collect all the x's. And the negative 4x and the positive 4x went away. 8x plus 4x gives us, where are we? Those two will give us plus 12x. Okay. And then we had that one constant minus 4. So this is what we get when we are asked to find k prime of x with 3 terms. And so that is our answer there. Okay. So I hope you enjoyed this section, and I hope you also have fun with all these problems. And I will see you in the next section. See ya.